Dear spectators, this video presents the article Similarity Search for an Extreme Application, Experience and Implementation. This article is published in the proceedings of the SISAP conference. My name is Vladimir and I wrote this article together with Tomáš, Raček, Aleš, Křenek and Pavel, Zezula. We all work at the Masaryk University in Brno, Czech Republic. Our article is application-oriented and figures a nice example of an interdisciplinary research. Our task was to develop a search engine efficiently evaluating similarity queries in the domain of the protein chains. Up to these days, proteins and protein chains are out of the main focus of the similarity search community. In fact, the search engine currently employed in a global protein databank is more or less optimized brute force sequential scan. Nevertheless, when we tried to apply contemporary similarity search techniques to this domain, we revealed several features which make it very challenging. Our article summarizes the challenging features of this domain in generic terms of the similarity search community. We discuss several state-of-the-art approaches and justify their pros and cons when dealing with the features of this domain. Then we propose and optimize our search engine, which we implemented as a web application. Our search engine can be used to search arbitrary metric data, and it greatly contributes to the search in spaces with expansive distance functions and spaces that suffer from the dimensionality curse. When solving the task to search the protein chains, we observed these features much stronger than in any other domain we had experienced before. Our article thus reports suitable ways to deal with them in general. Let me roughly describe the searched data. That is, what I learned from Tomáš, Raček and Aleš, Křenek. Proteins are important biomacromolecules, and each protein consists of one or more parts, so-called protein chains. Here you see a three-dimensional model of a protein chain. It consists of the balls and sticks, which represent atoms and bonds between them. Researchers have a hypothesis that protein chains with a similar structure have similar biological function. The structure of protein chains is quite complicated. Luckily, it can be simplified. There are so-called carbon alpha atoms, and their positions basically determine the coordinates of all other atoms within the protein chain. These carbon alpha atoms are often visualized as the ribbon, here in the green color. The similarity of protein chains thus can be expressed as the similarity of positions of their carbon alpha atoms. The BioID community traditionally uses the Q-score to express this similarity, so the bigger the value, the more similar protein chains. The range of these values is from 0 to 1. The whole formula is described in the article. We need to know just its complexity, which is given by a multiplication of counts of carbon alpha atoms in compared protein chains. This figures a problem that we will discuss. But first, let me describe the dataset that we want to search. We get the data from the protein databank, which is the biggest archive of the protein structures in the world. It has several versions with the same data, and we use the PDBe, that is, Protein Databank in Europe. It contains 500,000 protein chains, and it is a very important source of information for the whole community. Despite the importance and usage of this databank, the similarity search engine employed within the databank is extremely slow, evaluating similarity queries usually in minutes. To better understand the query execution times, we visualize the number of carbon alpha atoms in particular protein chains, and we denote them as the protein chain size. Specifically, we sorted all 500,000 protein chains according to their size. X-axis depicts their order, and Y-axis depicts the size of corresponding protein chain. All chains have from 10 to approximately 4,500 carbon alpha atoms, with extreme tail of biggest chains. Since the complexity of the Q-score evaluation is strongly affected by the size of compared protein chains, searching for the most similar protein chains to big query chain is potentially extremely time-consuming. For this reason, some heuristics are usually used to estimate the Q-scores, and they are usually very efficient. However, there are extreme cases in which even the heuristics fails to estimate Q-score efficiently. This is given by the fact that finding an optimum alignment of huge protein chains is a difficult task. This plot depicts the times of the most expensive Q-score evaluations which we have observed. While 98% of the Q-scores are computed up to 30 milliseconds, we observed about 1 per mil of Q-score computations that are evaluated in more than a minute each. The x-axis of this histogram depicts the time of a Q-score computation with the width of the bar 1 minute. 303 Q-scores, that is half of the per mil, took more than 10 minutes each. 10 Q-scores were evaluated in more than 42 minutes each. So what is the approach of the existing PDBe search engine to efficiently evaluate similarity queries? It goes through the whole database and just checks the sizes of the protein chains. For instance, if the chains are of sizes 30 and 100 carbon alpha atoms, their biggest possible Q-score is 0.3. It occurs if the smaller chain is precise subpart of the bigger one. Checking of the protein chain sizes thus can be adopted to skip some Q-score evaluations, and this is the only optimization employed in the current search engine. Moreover, current search engine checks the structure of the query chain, and if it is too big, the query execution is refused completely, even if near duplicates of the query chain are in the data bank. Extreme properties of the searched domain suggest simple solutions to speed up the search. First, we observed a long tail of the biggest protein chains, and at the same time, just big protein chains can be problematic to evaluate their similarity with others. Therefore, how about discarding biggest chains, similarly as the current search engine? We do not want to adopt this approach, since the PDBe databank is alive with tens of thousands protein chains newly added every year. The recently added chains are rather big, and thus inability to work with them figures an important drawback. Second, we observed that just a tiny ratio of the Q-score evaluations is extremely expensive, that is, evaluated in minutes. How about discarding long-lasting Q-score evaluations? This is also not a good idea, since even the Q-score of very similar protein chains can be evaluated in tens of minutes. Skipping these evaluations thus again causes an inability to evaluate similarity queries with big query chains. The search engine that efficiently executes similarity queries in this domain thus has to minimize the number of Q-score evaluations, especially in case of big query chains. The rest of this video presents our solutions to search this data. First, we transform the Q-score to the distance function. We simply subtract 1 minus Q-score to get almost metric distance function. The widely used heuristic to estimate the Q-score violates its symmetry, however. Even though these violations are rather small, they cause violations of the triangle inequalities. We thus need to adopt similarity search techniques that are robust enough to deal with these violations And we adopt pivot permutation-based techniques, that is, techniques that use a set of pre-selected protein chains called pivots to describe the positions of each protein chain by the order of its several closest pivots. Pivot permutation-based techniques bring us two other advantages. First, transformation of the Q-score to the distance function can be an arbitrary decreasing function, and it does not matter which one, since the permutation of the closest pivots is always the same. Second, pivot permutation-based techniques are also successful when dealing with the dimensionality curse presented here. Efficient search for k closest objects to the given query object, KNN for short, is possible just if closest objects to the query are close enough and if the distance function has a sufficient variance. Otherwise, the similarity query execution degrades to an evaluation to a majority of all distances between the query object and objects from the database. The distribution of the distances in case of protein chains is as extreme as almost 99% of distances are bigger than 0.8 and 90% of them is bigger than 0.9. This again motivates us to use pivot permutation-based techniques, as they are often reported to mitigate the dimensionality curse with a bigger success than techniques based on different principles. We also conveniently limit the permitted similarity queries, which is possible thanks to the following feature of the Q-score. Q-score directly describes the best alignment of two protein chains, so it well corresponds to the perceived similarity of chains. Therefore, the distance value is relevant and range queries are more semantically meaningful than in case of abstract similarity models, for instance, those from neural networks. According to the experience of the bio-IT community, distances above 0.5 describe as dissimilar protein chains, as they are mutually irrelevant. Our web application thus evaluates K and N queries with limited range. Considering the range of possible distances from 0 to 1, we implicitly limit the searching radius to 0.5, and we allow to extend it up to 0.7. Value k of KNN queries thus limits the maximum number of returned nearest neighbors. It can be set arbitrarily, and we use implicit value k equal to 30. The plot of the distance density could suggest that there are no distances as small as 0.5. Nevertheless, the histogram of distances with the logarithmic scale of the y-axis reveals that there are even these small distances. We confirm that 78% of query objects have 30 nearest neighbors in distance up to 0.5. Therefore, similarity queries with this limited searching radius are very meaningful. At this slide, I summarize our approach to search the protein chains, and in the following slides I will describe specific steps more in detail. First, we select a set of 512 pivots, and we evaluate all distances between the pivots and protein chains from the databank. This step takes about 3 weeks on a computer with 200 CPUs. We store this information in the database, and we use it up to 3 times during the query execution. Specifically, we provide users 2 times with the intermediate query results and then with the final results. We further speak about the phases of the query execution. The first phase uses the short sketches of protein chains in the Hamming space to select k-similar chains to the query chain. The second phase uses long sketches together with our probabilistic model to return more similar protein chains, and the third phase uses the advanced pivot permutation-based index together with long sketches and probabilistic model to return the top quality query results. Sketch of object O is a bit string in the Hamming space. Sketches compared by the Hamming distance approximate the search space, in our case the space of protein chains. We transform protein chains to their sketches by our transformation technique denoted here as the GHP50. It uses lambda instances of the generalized hyperplane partitioning to define sketches of length lambda bits. Considering all protein chains, here depicted by particular circles, we use a pair of pivots to split all the chains into two parts according to the closer pivot. This partitioning defines the value in the first bit of sketches of all protein chains. Then we consider another pivot pair to define another generalized hyperplane partitioning, and it defines the second bit of all sketches. Then so on and so on. The set of pivots and then the set of query objects used in the experiments is selected uniformly randomly by the protein chain size. It means that we sort all 500,000 protein chains according to their size, split the list into desired number of blocks, that is 512 in case of pivots, and pick a random protein chain from each block. The sketching technique GHP50 then selects pivot pairs to define approximately balanced bits of sketches that are pairwise low correlated. The long sketches that we use are of length 1024 bits. To define this sketching, we offered all 512 pivots to the heuristic selecting pivot pairs, and it used just 489 of them. The reason is that the smallest protein chains often define highly correlated bits, so they are not selected to define any pivot pair. To define the short sketches, we offered each 8 pivot out of those 512 preselected, that is, 64 pivots in total, to the heuristic defining pivot pairs for sketches. We observed that the heuristic is able to find 320 pivot pairs defining well-balanced and low-correlated bits, so these are the short sketches that we use in the first phase of the searching. Let us assume a query chain Q and the search for at most 30 most similar protein chains within the radius 0.5. In the first phase, just 61 distances between pivots and Q are evaluated to create a small sketch of Q. Then the engine evaluates all 500,000 Hamming distances to return 30 IDs of the protein chains with the most similar small sketches to the query sketch. All these Hamming distances are evaluated within a negligible time. At this point, the user interface starts to work asynchronously with the search engine. While the user interface starts parallel evaluation of all 30 Q scores between the query chain and the protein chains returned by the first phase, the search engine continues with the second search phase. We emphasize that the first phase returns IDs of the promising protein chains after 61 Q-score evaluations. Since all 61 pivots used to create a small sketch of Q are quite small, the first phase of the search is always very efficient. The computation of actual Q-scores of the query chain and returned answers can require some time in case of big query chains, but it is interrupted when the results of the second search phase are delivered. The second phase reuses evaluated distances of Q to pivots and evaluates other 428 pivot distances. This information is used to create a long sketch of Q, and the second phase searches just on long sketches. However, it uses also the probabilistic model to limit the search radius even in the Hamming space of long sketches. While this is just a small optimization in case of the second phase, it plays an important role in the third phase. So how we transform the search radius in the space of protein chains to the radius in the Hamming space? We used the probabilistic model published in our ACM Toys paper to define the mapping of the Hamming distances to the protein chain distances. Since the Hamming space is discrete, this mapping is a table of lambda plus 1 rows, where lambda is the length of sketches. Our model roughly estimates this conditional probability. Having sketches made by the GHP50 sketching technique that are within the Hamming distance B, then the original distance is at least t with the probability p. This value p is the only user-defined parameter, and we use p equal to 0.75, which is in compliance with the article where we proposed this probabilistic model. Please notice that this mapping is pre-computed and stored just once during the data pre-processing, so it is efficiently used in the main memory during the query execution. This table is the sketch of the actual mapping used in our web application. Please focus on the orange values at the right side. Hamming distance 340 is mapped to the distance of protein chains 0.5. Therefore, if the long sketches of length 1024 bits differ in at least 340 positions, then the distance of the original protein chains is at least 0.5 with a high probability. The second phase of the search uses this table and evaluates KNN range queries just on the long sketches. Then it returns a list of IDs of similar protein chains into the user interface, and here they are asynchronously processed. That means Q-scores are evaluated. At the same time, the third phase of the search is executed. In the third phase, remaining 23 distances between the query chain and the pivots are evaluated, and the pivot permutation-based index, called the PPP codes, is utilized to efficiently identify a set of 5,000 most promising protein chains in the database. We confirm that PPP codes work just with the IDs of pivots, so they are quite efficient. These 5,000 promising protein chains are checked by the long sketches. Specifically, having protein chain O, we evaluate the Hamming distance between its large sketch and the sketch of the query chain. If it is bigger than the Hamming search radius, given by the mapping of distances presented at the previous slide, O is discarded. Otherwise, we evaluate the distance of the query chain and O to see whether O qualifies to be in the current query answer. Finally, please notice the backward propagation of the decreasing search radius. If the query answer contains k protein chains, the searching radius decreases, and it means that also the Hamming search radius defined for long sketches decreases. Therefore, the power of the secondary filtering even increases during the query execution. For the median query chain, the secondary filtering by sketches filters out 4,810 protein chains out of 5,000 identified by the PPP codes. This box plot visualizes the variance over 1,000 randomly selected query chains. Therefore, to fully evaluate the similarity query on the dataset of 500,000 protein chains, our search engine needs to evaluate just 512 distances to pivots to filter out 99.962% of the dataset on median, and just 190 most promising protein chain remain. These are then processed sequentially. The searching accuracy expresses the ratio of the correct answer that was found. Here you see a nicely increasing accuracy over particular phases of the search. Again, the box plots depict values over particular query objects. The median accuracies are 47, 67 and 100% in case of the first, second and third phase respectively, and you see that the variance over query objects is quite big. The orange box plot depicts the results of the search engine currently employed within the PDBe database. This search can be even precise, but then it is even much slower, and here you see that this matters. Please notice that the y-axis depicting the query execution times is multiplied by 10 for each next box plot. Therefore, the first searching phase is finished in 0.18 seconds on median, first two phases are finished in 1.1 second on median, and all phases are finished in 2.5 seconds on median. The existing search engine evaluates queries in more than 3 minutes. That is, we are 73 times faster per median query object than the search engine employed in the PDBe databank. The most difficult query object is evaluated in 4 hours with the current search engine. So for these extreme query objects, our 3 phases of the search really pay off. The first results are delivered in 4 seconds. Then the second phase is finished in 12 minutes, and then the whole search is completed in 6109 seconds, which is 1 hour and 41 minutes. Since our online demo application visualizes the progress, users may decide whether they want to wait for the better results or the results of the lower quality are sufficient. Here is the link to our web application and the links to the searching techniques that we concatenate and employ to search the protein chains. Thank you for watching this video.